Hi everyone, in this lecture we are going to study again Fourier series of functions because they will be quite useful when we want to solve partial differential equations. So just a short summary of what we saw in the previous lecture. So if we have an f, a function, a 2p periodic function, piecewise smooth, that remember we are not going to really prove each time we find a function that we have a piecewise smooth function. In this course we are going to work always with this type of functions, so you don't have to prove that the given function in an exercise is piecewise smooth. We have the Fourier series of this f, the 2 periodic function, given by this formula that we have here, where we have these coefficients a0, an, and bn, and they are called the Fourier coefficients of f. And here we have these functions involved. Let's say that here we have a 1, here we have a cosine of n pi over p, where p is exactly the same p that we have here of this 2p periodic function of x, and then the other family of functions, sine of n pi over px. So assuming we have a 2p periodic function, we have this Fourier series representation of f, and we know how to compute these coefficients, the Fourier coefficients of f, with the Euler formulas that we saw last lecture. They are given by these integrals here. The first one is maybe the easiest one, where we only integrate f between minus p, and we have this factor in the front. And then computing the other coefficients is just f times cosine and f times sine, but we have this for each n. Okay, so just for you to notice, these coefficients are exactly f times the function that is next to each coefficient. So if we go back to the Fourier series representation, a0 is exactly f times 1, and 1 is here. An is exactly f times cosine of n pi over px, which is there. Okay, and then you have to remember the factor in the front changes a little bit, but it's mainly in this way how we compute these Fourier coefficients. Okay, and the last one, the f with sine for each n. And we also saw that for the points where f is continuous, we can have this Fourier series representation exactly equal to f at x. And that means that the Fourier series converges to fx. When we don't have this continuity, so f is discontinuous at x, then we don't have exactly the identity to fx, but we know that the Fourier series converges to this average between the right and left limits. So recall this notation. This is the right limit, which is here. We approach this x from above here, and the left limit, that is here, we approach f from below. In the example that we saw last week, this was the jump of the function, where the function was discontinuous. This number is related to that jump that we have in the graph of the function. Okay, so in other words, what we have is the Fourier series representation is exactly f at x if f is continuous at this point x. And the Fourier series representation of f is this average when the point is a discontinuity point for f. Okay, so now we are going to see how to vary the period of a Fourier series, and that will be useful because this will be a possible situation that we find in exercises during the course. Imagine that we have two functions, f and g, and they are periodic functions. And then they might have different periods. And imagine that we know one of the Fourier series representation. So we have these two functions, f and g, with different periods, and we know the Fourier series representation of f. But you know what? F and g are quite similar. So we wonder if, since we already know the Fourier series representation for f and g are so similar, can we deduce the Fourier series representation of g from the Fourier series representation of f? Okay, so the answer will be sometimes, and we will see an example to illustrate this idea. Okay, so this is all about trying to recycle information, let's say, because we have two functions, f and g, too similar, let's say, and we know the Fourier series representation of one of them. So we wonder if we can recycle that information and get the Fourier series representation of g. So we don't have to compute everything from zero, let's say. Because to have the Fourier series representation of f, remember that we have to compute these Fourier coefficients, so that involves these three computations, let's say, because we need to check, we need to compute a0, we need to compute an, and we need to compute bn for each possible n natural number. So if we don't want to do that from 0 again for the function g, and we want to recycle the information that we have for f, since f and g are so similar, we are going to see an example where we actually can do this recycle thing. Okay, so just one more comment before the example. Last lecture we found the period of this function cosine of x over 4 using that we know the period of cosine, right? And we also saw this general property that if we have a function which is t-periodic, then if we modify this function in this way, x over a, then we know that this new function has period a times t. So the idea of this example is that given a periodic function, we can vary its period with a change of variables. And that will be the key when we have two very similar functions and we already know the Fourier series representation of one of them. These guys, this f and this g, we can for sure say that they are quite similar, right? Okay, so maybe in this first comment, this is too obvious. Maybe in the example that we are going to see, it's not quite obvious, but hopefully with practice you will notice when you are allowed to use this technique. Okay, so let's go into the example. We have this function g, and maybe you remember from last lecture This is so similar to the fourth example that we saw when we were studying periodic functions. You can check that later. But okay, let's continue with this example. We have a letter C that is just a positive constant, and this piece of line can be written in this way. It's C1 minus x over p. You can check that when x is 0, we take the value c, and when x is 2p, we take the value minus c here. Okay, and then since this is a periodic function, it repeats itself out of this interval of length 2p. Okay, so here we have the description of the function and the period that here is 2p. And as I was saying, this function looks so similar to f, this f that we saw last week, which is a 2 pi periodic function, okay? And if you go back to the lecture 3, there we compute the Fourier series representation of f, and we got exactly this. And we have this identity for every point between 0 and 2 pi. So, this is the question. We have f and g, quite similar functions, and we already know the Fourier series representation of f. So we wonder if with this information that we already have, we can do some computation, but not from 0, like every coefficient, Fourier coefficient of f, and we can recycle this information to find the Fourier series representation of g. Okay, so the answer will be yes, we can, and that's why we are seeing this example. And we have to work a little bit with the expression that we have to find the relationship between f and g. So, what can we do here? We know this identity for these values of x. X between 0 and 2 pi. Here is x, and what we did in this step, from this line to this line, the only change is that we have this pi like a common factor. So this guy becomes x over pi. And now we notice that, okay, we are being similar, let's say, to g, because she was like 1 minus x over p instead of pi, and there was a constant here, c. So here is the expression of g, and we changed the variable just to work better here in the exercise. So she was this constant c, 1 minus y over p. And we are trying to rewrite f in such a way that we can find a relationship with g, the function g. Okay, so the first step here was just this pi as a common factor of the expression. And then looking at these two guys, it would be nice if we get this x over pi equal to y over p. So we will have almost the expression of g there. So that is what we are going to do. We kind of force this identity. Then x should be this guy, pi over p times y. And notice that in the case that y is between 0 and 2p, this guy x belongs to the right interval. Why? If we multiply this inequality by pi over p, which is what we need to get x here, we get 0 in this size and 2 pi in this size. So we have that for every y in this interval, 0 to p, we get that this new guy, pi over p times y, belongs to the interval 0 to pi, which is exactly the interval where we have the Fourier representation of f. So those values satisfy the Fourier representation of f. Maybe here we have of f. Okay. So we can replace x in the Fourier representation by this new candidate, new x, because it's a admissible value. And what happens is if we do that, let's check our calculations. So we knew this identity. Here is f, and here is the Fourier series representation of f, where x belongs to this interval 0 to pi. Now, this is a possible x, so we just replace x by this guy. And okay, here there is nothing we can solve, let's say, but in this size of the identity, we can work just a little bit. So this pi goes away, and we get exactly a piece of of g. And the only things that we need to add is this constant c. So we can multiply and divide by this constant c, and suddenly we get the expression g of y times this constant pi over 2c. And we have this identity for every y between 0 and 2p. So what do we get? G of y is equal to this constant, because we can just put this constant to the other side of the identity. If you look here, the identity starts in this way. We continue here, 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 and we go down. So what we finally get is that g of y is equal to 2c over pi, and this expression. And we have this for every y between 0 and 2p. And we can also go back to the letter x if we want, but okay, it's the same. So g of x is this constant and this guy here. So what we just did is we have two functions, f and g. They are quite similar, and we know the Fourier representation of one of them. So we recycle that information to get the Fourier representation of g without computing each Fourier coefficient with the Euler's formula. We only recycle the information that we already had with this, which is the Fourier series representation of f. And how we do that? We just try to find the relation between the function f and g. That notice that what we did is just a change of variables, right? What are we doing here is just a change of variable. And we have to make sure that the new guy belongs to the right interval, because we need these new values, pi over p times y, to be an admissible x where we know the Fourier representation of f coincides with the function f. That's the only maybe a step that you have to justify apart from the relation of f and g, between f and g. Okay. And that's it for the first part of this lecture.